Hello and clear skies, everyone, and welcome to York Observatory TeleTube, the online astronomy and astrophysics program written and presented by the students, faculty, alumni, and friends of York University. I'm Quinton, and I'm joined tonight by Amin, Guggen, and ANITA. We are broadcasting live from the Alan I. Carswell Observatory located at York University in Toronto, Ontario, Canada. York TeleTube broadcasts every Wednesday night at 7:30 p.m. local Toronto time. But if you can't make it to one of our broadcasts, don't worry. All of our TeleTube events are recorded and uploaded to our YouTube channel for you to watch at whatever time works for you. If you have any questions about the material covered in tonight's show, please feel free to ask them in the live chat, and we will try our very best to answer them over the course of the night. If you have any questions or comments about our past shows, or if you have suggestions for future topics, please send us an email at observe@yorku.ca. You can also connect with us on Twitter or Instagram with the handle @York Observatory and on Facebook at Alan I. Carswell Oz. All right, so now it's time to turn our gaze outward and investigate some of the fascinating objects that lie beyond the 8 planets. Amin, Guggen, ANITA, and myself are excited to deliver to you a presentation about dwarf planets and the outer solar system. I'll hand the reins over to Amin now to get us started with a deceptively simple sounding question. What is a dwarf planet?
So, what is the difference between a planet and a dwarf planet? To begin with, the classical definition of a planet is that it is an astronomical body that orbits a star. It must also be able to have enough gravity to pull itself into a round shape, and crucially, according to the International Astronomical Union, it must have cleared its neighborhood region of other objects. This last definition came at a time when multiple Pluto-sized objects were found in the outer solar system. We can't just call all of them planets, and so the decision was made to create a new category of object, the dwarf planet. A dwarf planet meets the first 2 criteria of a planet, but not the third. Pluto, for example, cannot clear its neighborhood and actually weighs less than the other objects scattered around its orbit. Dwarf planets are usually found beyond the last planet Neptune, with the exception of Ceres. 5 of them are officially recognized, with dozens in consideration, and possibly hundreds or even more remain yet to be discovered. The total number is unknown because either a spacecraft has to fly by the object in consideration in order to verify that it is round in shape, or the object must have a moon, which can allow scientists to compare the moon to the object and estimate the density of it and deduce its shape from that. Pluto is located 39.5 astronomical units away from the Sun, with 1 astronomical unit being the distance from Earth to the Sun. The other dwarf planets are a little bit further away, except for Ceres, which is located in the asteroid belt between Mars and Jupiter. Apart from Ceres and Pluto, which I already mentioned, the recognized ones are called Ceres, Haumea, and Makemake. Now I'll go over all the dwarf planets individually, except for Pluto, which will come later with another speaker. To begin with, we'll start with Ceres. Ceres is located 2.8 astronomical units from the Sun, inside the asteroid belt. It is the only dwarf planet to be inside the orbit of Neptune. Despite being almost 1/3 of the mass of the asteroid belt, it is much smaller than Earth's moon. It is named after the Roman goddess of harvests. 1 year on Ceres is 4.6 Earth years, but 1 Ceres day is just 9 hours. It was initially thought to be an asteroid, but scientists classified it as a dwarf planet in the end due to its size in 2006. Ceres has a radius of 476 kilometers. It has no moons, unlike the other known dwarf planets. It is the first dwarf planet to be visited by a spacecraft. The Dawn craft visited it in 2015 in order to study its surface, composition, and history. This craft is seen in the slide on the right. Because Ceres contains water, scientists are interested in studying it as a potential harbor of life. The surface is heavily cratered and there's a lot of ice underground. Next, we will go over the dwarf planet Makemake. Makemake is located 45.8 astronomical units from the Sun. It takes sunlight 6 hours and 20 minutes to travel from the Sun to Makemake. Like the rest of the dwarf planets besides Ceres, it is located in the Kuiper belt, which is a region beyond Neptune. Another term for these objects is the trans-Neptunian objects. It is slightly smaller than Pluto and is the second brightest object in the Kuiper belt after Pluto. 1 year on Makemake is 305 Earth years, and 1 rotation or day is 22.5 hours, which is similar to that of Earth and also Mars. We know very little about the structure of Makemake since there has not been a spacecraft mission that visited it. Its color appears to be reddish-brown, similar to Pluto. Methane and ethane have been detected on the surface. The surface is extremely cold, being negative 243.2 degrees Celsius, and so the presence of life is unlikely. Makemake has one provisional moon called MK2. Provisional means that it has not been properly named yet because it was just recently discovered. Makemake itself was discovered in 2005 by the Palomar Observatory, and in 2008 it was recognized as a dwarf planet. Up next is Haumea. Haumea is located 43 astronomical units from the Sun. Sunlight arrives in 6 hours. It is also located in the Kuiper belt. It has an oval shape with a radius of 620 kilometers. That makes it just under 10 times smaller than Earth. Haumea has 2 moons called Namaka and Hi'iaka. 1 year is 285 Earth years, and 1 day on Haumea is only 4 Earth hours, making it one of the fastest rotating large objects in the solar system. This fast spin makes Haumea distorted into a football-like shape. Its name comes from the Hawaiian goddess of fertility. Haumea is largely made of rock with a coating of ice. We know very little about the surface or atmosphere. With an extremely cold surface, life is probably impossible here too. In 2017, it was discovered that Haumea has rings, making it the first Kuiper belt object we know of to have them. The dwarf planet was discovered in 2004 and its moons in 2005. The International Astronomical Union recognized it as a dwarf planet in 2008. Eris, the last one to be mentioned here, is in the scattered disk, not the Kuiper belt, more on that later, and is located 68 astronomical units from the Sun, making it the most distant recognized dwarf planet. It takes sunlight more than 9 hours to reach Eris from the Sun. It has a radius of 1,163 kilometers, making it around the same size as Pluto, but it's 3 times as far from the Sun compared to Pluto. It takes a whopping 557 Earth years for Eris to make 1 trip around the Sun. 1 rotation takes 25.9 hours, which is similar to our Earth day. Eris is named after the Greek goddess of discord and strife. Its discovery prompted debate because it seemed to be larger than Pluto at first, calling into question Pluto's designation as a planet. As we know, the term dwarf planet was later defined, and Eris was recognized as one in 2006. We don't know much about its internal structure. The surface is probably rocky like Pluto's. The surface temperature is somewhere around negative 217 to negative 243 degrees Celsius. Because of Eris's distance from the Sun, it is very cold, and the atmosphere often collapses and freezes into snow. It has 1 moon called Dysnomia. We don't know how many dwarf planets there are in the solar system. The highest estimates are 200 in the Kuiper belt and over 10,000 beyond the Kuiper belt. There are currently hundreds of possible candidates. In order to qualify as a dwarf planet, a celestial object must have hydrostatic equilibrium. This happens when gravity is balanced by outward pressure, creating a round shape. This arrangement can be verified by a spacecraft. Flyby missions are being planned in the future to visit dwarf planets. In July of 2015, NASA's New Horizons became the first spacecraft to visit Pluto. New Horizons will also visit other objects in the Kuiper belt until it runs out of fuel. For now, most of what we know about the Kuiper belt comes from ground-based telescopes and the Hubble Space Telescope. On the left of this slide, some trans-Neptunian objects can be seen. This list also includes small solar system bodies, of which there are many. There's also the hypothetical Planet 9 to be considered. This is a possible planet which might cause gravitational effects that may explain the strange orbits and other features of some trans-Neptunian objects. It has not been observed yet, but is theorized to exist. To conclude this section, many more space missions are required in the future in order to learn more about the objects in the outer solar system. And now Gagan will be taking the mic to discuss the most prominent dwarf planet, Pluto.
Thank you, Amin. Now there's one dwarf planet in particular that I'm sure you're all familiar with, and that's Pluto. Pluto's planetary status has been the subject of hot debate among almost all astronomers, including those of us at the observatory. Our coordinator is a staunch proponent of Pluto's status as a full planet, but unfortunately for her, Pluto is officially considered a dwarf planet. Pluto is a rocky dwarf planet in the Kuiper belt, a ring of solar system bodies that lies beyond Neptune's orbit. It was initially discovered in 1930 and was dubbed the 9th planet of the solar system but that title has since been revoked. I'll go into more detail about why in a few minutes. Pluto is the largest Kuiper belt object in volume ever observed and the first one ever identified. Most of the research and imaging done for Pluto has been recent, due mostly in part to its distance from Earth. For a long time, the blurry images on the left were all we had, until New Horizons completed its flyby of the Pluto system in 2015, taking the iconic Pluto picture with the heart-shaped plane front and center. Before we get into what we know about Pluto, let's start at the beginning. How was Pluto discovered? For a while after Neptune's discovery in 1846, which was done through analysis of gravitational effects on Uranus' orbit by another solar system body, astronomers wondered if there was more in the solar system that they could not yet see. In the early 1900s, an astronomer named Percival Lowell decided to go on a thorough search for a ninth planet, which he called Planet X, using a slight gravitational effect on Uranus and Neptune as the basis for his calculations. However, his search was unsuccessful. Following his death, another astronomer, Clyde Tombaugh, was assigned to the project and used a slightly different approach to try and identify a possible ninth planet. Tombaugh imaged the same portion of the night sky repeatedly and analyzed the images to determine if any objects were moving in comparison to the relatively stable background stars. In 1930, his project yielded the discovery of a ninth planet beyond the orbit of Neptune in a location that was in close accordance to Lowell's predictions, which we now know as Pluto. The funny thing about this discovery is that Lowell's prediction of Planet X and Tombaugh's discovery of Pluto in a similar area were most likely coincidental. Neptune's mass was later reanalyzed and updated to be slightly lower than its original estimate, and recalculations of Neptune's gravitational effects on Uranus' orbit showed that there was no longer a Planet X needed to explain the orbit. As we conducted more and more research on our solar system and began to learn more about planets, it became increasingly clear that Pluto was an outlier in more ways than one. While the solar system's 8 main planets have orbits that lie on a relatively flat plane around the Sun called the ecliptic, the plane of Pluto's orbit is tilted at a substantial angle from the ecliptic. This can be seen in the animation on the left. The white line shows the planets and their orbits on the ecliptic, and Pluto's orbit is shown in red. Pluto's orbit is also much less circular than the orbits of other planets, and it is trans-Neptunian, which means that the orbit actually crosses Neptune's orbit. Like Amin mentioned earlier, another criterion for a planet is that it clears its neighborhood, meaning that it is the only large body in its orbital neighborhood. Pluto does not meet this criterion.
Now we'll just have to maybe take a short break, as we say, and Quentin, are you wanting to hop in?
Yeah, I'm sorry. I'm sorry about the technical difficulties, Guggen. I think that I could finish telling the audience about Pluto if you want.
I think that might be a wise idea. So we're just finishing up the reclassification of Pluto as a dwarf planet. And I believe we talked a little bit about, as we were just saying, since the 1990s, more and more of these Pluto-like bodies have been found in the Kuiper belt, sort of adding to the case against Pluto's planetary status.
Of course. Yes, so as Professor Hyde just mentioned, since the 90s, more Pluto-like bodies have been found in the Kuiper belt. And this did add to the case against Pluto's planetary status. In 2006, after years of debate, the International Astronomical Union set a new classification guide for planets, as Amin went over earlier. Pluto did not make the cut and was so demoted to a dwarf planet. While the classification criteria have been and are still under heavy debate, it remains much more practical to demote Pluto than it is to promote all the other Pluto-like Kuiper belt objects to full planets. Now that we know how Pluto was discovered and reclassified, let's learn a little more about Pluto itself. This may surprise you to know, but Pluto is smaller than our moon. Pluto's diameter is only about 70% of the moon's diameter. Pluto consists of a dense core surrounded by a water ice mantle and crust. Recent research also indicates evidence that a subsurface liquid water ocean also exists under the crust, produced by internal heating. Pluto has a thin atmosphere consisting mostly of nitrogen, methane, and carbon monoxide, and the surface is extremely cold owing to its distance from the sun. In fact, Pluto's surface temperature can dip below -240 degrees Celsius. In comparison, the coldest temperature ever recorded on Earth was -89 degrees Celsius in Antarctica. Interestingly, Pluto is so cold that the mountaintops, which are closer to the sun, are warmer than the valleys and plains. Because of the difference in temperature, Pluto's mountaintops are white due to condensation from the atmosphere, but the low altitude regions of Pluto are so cold that they are too cold for this kind of snow. Since recent missions, such as New Horizons, have provided us with excellent detailed imagery of Pluto's surface, we've been able to discern different landforms as well. For example, the Sputnik Planitia is a wide basin filled with frozen nitrogen and carbon monoxide and forms the left side of Pluto's so-called heart. The ice in the basin forms cells, which can be seen in the image at the center of the slide. We are even able to discern mountains and valleys on the surface of Pluto, such as those on the right. Pluto also has an interesting orbit. It takes Pluto about 248 years to orbit the Sun, which means that since its discovery, it has yet to complete one full orbit. Compared to the other planets, which orbit on the flat ecliptic plane, Pluto orbits the Sun at an angle of about 17 degrees to the ecliptic. Pluto's orbit is also trans-Neptunian, which means it intersects Neptune's orbit, but don't worry, their orbits are angled such that Pluto and Neptune will never actually collide. The closest distance possible between Pluto and Neptune is actually 17 times the distance from Earth to the Sun. So it's safe to say that there won't be any close calls anytime soon. Even though Pluto is a pretty small solar system body, it actually has a moon system with 5 satellites orbiting it. The largest of these satellites, Charon, is actually large enough in size compared to Pluto that they are sometimes considered a double dwarf planet system. And their shared center of mass, or barycenter, is a point in space between them. Pluto and Charon both orbit around this barycenter, rather than Charon orbiting around Pluto outright. This can be seen in the animation on the left. Pluto's other moons are Styx, Nix, Kerberos, and Hydra. These 4 moons resemble asteroids rather than a typical spherical moon. All 5 of Pluto's moons are shown to scale on the right. Pluto's moons are thought to be created by a collision of Pluto and another body, similar to the collision theory of our moon's formation. Since Pluto's discovery, there have been numerous efforts to image it and conduct more research. Hubble took some of the first images of Pluto, albeit with low resolution. One of the most notable missions to Pluto is New Horizons. New Horizons was launched in January 2006, shortly before Pluto was reclassified as a dwarf planet. The primary mission objectives were to study Pluto's and Charon's physical characteristics, including surface features, atmosphere, and chemical composition. The comparison in detail from some of Hubble's first images, shown on the right, and the images taken by New Horizons is astounding. New Horizons was able to capture detailed images of specific surface features that gave insight to Pluto's structure and composition as well as its atmosphere. The New Horizons mission has since extended its operational run and continues to provide us with information on other, more distant Kuiper belt objects. It will eventually leave the solar system. Now, ANITA will teach you more about the far reaches of the solar system beyond Pluto.
Thank you, Clinton. Now, Pluto is probably the most famous deep solar system object, but that doesn't mean that the solar system ends once you cross its orbit. The truth is that there are plenty of interesting objects and phenomena that can be seen out in the far reaches of Sun's gravitational pull. In this section, I'll be detailing what we think we know about the major regions of the outer solar system, such as Kuiper belt, a scattered disk, and Oort cloud. And I'll be explaining where this data comes from. The Kuiper belt is a disk-shaped region of the solar system extending from the orbit of Neptune to about 50 astronomical units from the Sun. Although it is 20 times wider than the asteroid belts between the orbits of Mars and Jupiter, there are similar in the sense that they are both composed primarily of small bodies and leftover debris from the formation of the solar system. Kuiper belt objects contain high concentration of ices such as methane, ammonia, and water. Many of the objects mentioned previously in this presentation are considered to be a part of the Kuiper belt. These include the dwarf planet Pluto, Makemake, and Haumea, as well as the unconfirmed dwarf planet candidates such as Quasar and Orcus. An object in the Kuiper belt is only able to remain there if Neptune's gravity does not interfere with its orbit. So many Kuiper belt objects have to be in orbital resonance with Neptune. For example, the Plutinos are a particularly stable group of Kuiper belt objects that form in the inner part of the belt and orbit the Sun twice for every 3 orbits that Neptune makes. There are only 2 possible locations for Neptune to be when a Plutino makes its closest approach to the Sun. And as long as both positions are sufficiently far away, the object will perpetually miss Neptune and avoid being pulled out of its orbit. Around a quarter of all known Kuiper belt objects are Plutinos, including Orcus and Pluto, after which the group is named. At the outer edge of the Kuiper belt, there are Tutinos, which orbit the Sun once for every 2 orbits of Neptune, and beyond this point, far fewer objects have been found. There are also important complicated orbital resonance that can exist, although these are less important. Kuiper belt objects are not in orbital resonance with Neptune are called classical Kuiper belt objects, or QB1s. Notable classical Kuiper belt objects include Quasar, Makemake, Eriketh, which was visited by the New Horizons spacecraft in 2019, and formerly Haumea, although more recent evidence suggests it may actually be in a resonance orbit after all. The classical Kuiper belt objects have orbits that remain undisturbed by Neptune, while the resonant Kuiper belt objects are able to stay where they are because their orbital harmony helps keep them away from it. But not all distant objects are able to enjoy this peaceful coexistence. All right, this animation demonstrates the orbital resonance of Orcus and Pluto against Neptune. Neptune, which is the white dot at 5 o'clock, is held stationary while the other objects move relative to it. Here, Pluto is gray and Orcus is red, and notice how their paths move relative to Neptune so that they're always far away from it. Even though at some points they are closer to the Sun at the center than Neptune is. Also, the rings in the middle are the orbits of the other gas giants. The scattered disk is a more sparsely populated disk of outer solar system objects, which is much irregular orbits. It is believed that the scattered disk consists of former Kuiper belt objects that got close enough to Neptune for its gravity to affect them, launching them out into a highly eccentric orbit that can make them hundreds of astronomical units away from the Sun before returning to Neptune's orbital distance at 30 astronomical units. These objects typically have very highly inclined orbits as well, being on an angle of up to 40 degrees compared to the orbits of other planets. By comparison, 2/3 of all classical Kuiper belt objects have orbital inclination of less than 5 degrees. Furthermore, whenever objects in the scattered disk pass near Neptune's orbit, they run the risk of having their paths perturbed even more. This can result in them getting thrown out to the Oort Cloud or getting sent toward the inner solar system. It is believed that the Centaurs, which is a set of icy objects with orbits in between Jupiter and Neptune, originated from the scattered disk. The dwarf planet Ceres also belongs to this set of objects. Out beyond the edge of the Sun's heliosphere lies a theoretical region of space called the Oort Cloud, believed to lie at distances ranging from 2,000 to 200,000 astronomical units. These icy objects form the very edge of the Sun's gravitational sphere of influence. With a maximum distance of 3.2 light years from the Sun, the Oort cloud would be 1,000 times more distant than the Kuiper belt and scattered disk. Unlike the Kuiper belt, which is shaped like a disk and mostly lies in the same plane as the planets, the outermost Oort cloud object would be scattered in a sphere around the Sun, orbiting with a wide range of inclination angles with respect to the solar system. At distances this great, Oort cloud objects would be only weakly bound to the solar system and could have their orbits perturbed by other nearby stars. This could either cause them to fall down into the inner solar system, passing by the Sun in an extremely elliptical orbit, or it could cause them to escape the Sun's sphere of influence entirely, entering into the orbit around a star or drifting through interstellar space for millennia. While the Oort cloud, if it exists, is in mind-boggling distance, astronomers believe that most of the material that might make it up would have formed much nearer to the Sun and subsequently been scattered by the giant planets in a more extreme version of what happened to the scattered disk. The existence of the Oort cloud was hypothesized in order to explain the behavior of long-period comets. These comets have orbits several thousand astronomical units in size, and unlike the short-period comets that likely originated from the scattered disk and orbit close to the elliptical plane, they approach the Sun from all different directions. The orbit of comets are not stable, so these objects cannot have formed in the orbits that they currently possess. Rather, the simple explanation seems to be that they enter the inner solar system from a region of space thousands of astronomical units away and are able to do so from any angle because they're distributed spherically around the whole sky. That's the end of our exciting IC show for tonight, but we will be around to answer questions live here on YouTube chat for the next few minutes. So make sure to ask your questions from our helpful crew, and we have been here with our team, Quentin, Gagan, and myself, Anita. You have been listening to Alumni Carswell Observatory's weekly TeleTube broadcast, the Astronomy and Astrophysics program written and presented by the students, faculty, alumni, and friends at York University. Make sure to leave any comments or question in the comment section of the video. And if we miss your questions during the live, just comment on the chat. You can always connect with us on Twitter and Instagram with the handle at York Observatory and on Facebook at Alumni Carswell Obs. All of our programs are free, but if you would like to make a donation, please see our website at observatory.info.yorku.ca. Thanks for tuning in, clear skies, and have a good night.